Hello viewers, welcome to my channel Maths with VTC. In this video class, I am going to teach you polynomials. Now let us see the mathematical definition of polynomial. A polynomial is an expression that consists of variables, terms, exponents and constants. Now let us recollect the difference between variables and constants. Consider this triangle. This is an arbitrary triangle. A, P and C are the angles. They can assume any value, but a plus B plus C is equal to 180 degree. Whatever the triangle is, whatever A, B and C may be, but their sum is always constant. Therefore, A, B, C are variables, but A plus B plus C is equal to 180, which is a constant. Let us see one more example. This is a circle with a diameter D. Then the ratio between the circumference and the diameter is always a constant. Whatever the diameter of a circle be, the ratio between circumference and the diameter is always a constant. Therefore, the diameter is a variable, circumference is a variable, but the ratio between circumference and the diameter is always a constant. So, there is a difference between variables and constants. Now, let us see some examples for polynomials. 2x plus 9. This is a polynomial. It has two terms and the variable is x. 2 and 9 are constants. X square plus 3x plus 11. Three terms are there. X is the variable. 3 and 11 are constants. Now, for each polynomial, we can associate a positive integer that is called a degree of the polynomial. What is its definition? If p of x is a polynomial in x, the highest power of x in p of x is called the degree of the polynomial p of x. Now let us see some examples. 4x plus 2 is a polynomial in x. What is the highest power of x? It is 1. Therefore, its degree is 1. Consider 2y square minus 3y plus 4. It is a polynomial in the variable y. What is the highest power of y? Obviously, it is 2. Therefore, degree of this polynomial is 2. Consider 5u cubed minus 4u square plus u minus square root 2. It is a polynomial in u. What is the highest power of u? 3. Therefore, it is of degree 3. Consider these expressions. 1 by x minus 1. It is a fraction. In denominator, you have polynomial x minus 1, but it is a fraction. Therefore, overall, it is not a polynomial. Square root of x plus 2. Definitely, this is not a polynomial because the variable x is in the radical sign. Therefore, these kind of expressions are not polynomials. Now, a polynomial of degree 1 is called a linear polynomial. For example, 2x minus 3, root 3x plus 7. Root 3 can be there because it is only a constant. Root 3x plus 7, y minus square root of 11. All these things are linear polynomials. Next, a polynomial of degree 2 is called a quadratic polynomial. For example, 2x square minus 3x plus 1 by 7, u square minus 2. All are quadratic polynomials. Now let us see cubic polynomials. A polynomial of degree 3 is called a cubic polynomial, and these are the examples. 2 minus x cube is a cubic polynomial. Y cube, this term alone is a cubic polynomial. Square root of 2 into x cube plus 3x square minus 7. It is a cubic polynomial. Similarly 3x cube minus 2x square plus x minus 1 is also a cubic polynomial. Now let us see the general form of polynomials. A linear polynomial is always of the form ax plus b. So ax plus b is the general form of a linear polynomial. Ax square plus bx plus c. This is the general form of a quadratic polynomial. Ax cube plus bx square plus cx plus d. It is the general form of a cubic polynomial. In all cases, a not equal to 0. For example, if a is equal to 0 here, it is no longer a cubic polynomial. So to ensure that it is a cubic polynomial, a must not be 0. Now what is value of p of x? If p of x is a polynomial in x and if k is any real number, then the value obtained by replacing x by k in p of x is called the value of p of x and it is denoted by p of k. So p of x is a polynomial. You just replace x by a number k, then you get a value that is denoted by p of k. Let us see some example. You take p of x is equal to x square minus 3x minus 4. Then p of 1 is equal to, you just replace x by 1, you get 1 square minus 3 into 1 minus 4 which is equal to minus x. So this minus x is the value. P of 0. So you replace x by 0, you get 0 square minus 3 into 0 minus 4 which is equal to minus 4. Similarly, P of 4. It is equal to 4 square minus 3 into 4 minus 4 which is equal to 0. So it has a significance because 4 makes P of x 0. Therefore, we get a new definition. A real number k is said to be a 0 of a polynomial P of x if P of k is equal to 0. That means what? Here 4 is a 0 of x square minus 3x minus 4 because when you substitute x is equal to 4, this polynomial becomes 0. Now we are going to see the geometrical meaning of the zeros of a polynomial. We start with a linear polynomial 2x plus 3. To find its geometrical meaning, first you take y is equal to 2x plus 3 and plot the points of y is equal to 2x plus 3 on the Cartesian plane and draw the graph. How to plot the points? You look at this table. So x, y is equal to 2x plus 3. I give the value x is equal to minus 2, then y is equal to minus 1. When x is equal to 0, y is equal to 3. When x is equal to 2, y is equal to 7. We can draw the graph. Using these 3 points, we can draw the graph. Since it is a straight line, only 2 points are enough, but I have plotted 3 points. You look at this figure. This is the line y is equal to 2x plus 3. Now, you observe that this straight line y is equal to 2x plus 3 cuts the x-axis at x equal to minus 3 by 2. So you can observe that this straight line y is equal to 2x plus 3 cuts the x-axis at x is equal to minus 3 by 2. But what is minus 3 by 2? When you substitute x is equal to minus 3 by 2 in this polynomial, you get 0. Therefore, it is nothing but 0 of the polynomial 2x plus 3. What do we infer from that? If k is a 0 of a polynomial, then the corresponding graph cuts the x-axis at k. This is the geometrical meaning of zeros of a polynomial. Now you can generalize it. In general, for a linear polynomial ax plus b, where a not equal to 0, the graph y is equal to ax plus b is a straight line which intersects the x-axis at exactly one point, namely minus b by a, 0. Therefore, the linear polynomial ax plus b has exactly 1, 0, namely the x-coordinate of the point where the graph y is equal to ax plus b intersects the x-axis. Now let us consider a quadratic polynomial, x square minus 3x minus 4. So to draw the graph, we take y is equal to x square minus 3x minus 4. Let us find some points on the graph y is equal to x square minus 3x minus 4. To obtain the points, I substitute x is equal to minus 2, then I get y as 6, x is equal to minus 1, y equal to 0, x is equal to 0, y equal to minus 4, and so on. But from the above table, you can see when x is equal to minus 1, y becomes 0. When x is equal to 4, y becomes 0. That means what? Minus 1 and 4 are zeros of the polynomial x square minus 3x minus 4. Now, this is the graph of y is equal to x square minus 3x minus 4. Look at carefully. This graph, actually it is a parabola open upwards. It cuts the x-axis at minus 1, 0 and 4, 0. So minus 1 and 4 are the x-coordinates of the points where the graph y is equal to x square minus 3x minus 4 intersects the x-axis. Thus, the zeros of the quadratic polynomial x square minus 3x minus 4 are x-coordinates of the points where the graph y is equal to x square minus 3x minus 4 intersects the x-axis. So this fact is true for any quadratic polynomial. That is, the zeros of a quadratic polynomial ax square plus bx plus c, a not equal to 0 are precisely the x-coordinates of the points where the parabola representing y is equal to ax square plus bx plus c intersects the x-axis. In general, the shape of the graph y is equal to ax square plus bx plus c can be any one of the following three cases. Let us see one by one. Case 1. Now you look at the diagram. The parabola cuts the x-axis exactly at 2 points. But in the first diagram, the parabola is open downwards like this. And in the second diagram, the parabola is open upwards. The fact is, it cuts the x-axis exactly at 2 points. Therefore, the polynomial has 2 zeros. Now you look at case 2. In both the diagram, the parabola touches the x-axis at exactly 1 point. Here it touches, here also it touches, but here the parabola is downwards, here the parabola is upwards. Therefore, in this case, the number of 0 is only 1. Now let us see the last case. From this diagram, you can see that the parabola does not intersect x-axis. Here it is open upwards, but it does not touch the x-axis. Here also it is open downwards, but it does not touch the x-axis. So in this case, the polynomial has no zeros. And all the three cases carefully, okay? Now we go to cubic polynomial. Consider the polynomial x cube minus 4x. You take y is equal to x cube minus 4x and find the points like this. X is equal to minus 2, y equal to 0, x equal to minus 1, y equal to 3, and so on. From the above table, you can easily verify that minus 2, 0, and plus 2 are zeros of the cubic polynomial because at those values, y is equal to 0. Now, this is the corresponding graph of the equation y is equal to x cube minus 4x. It cuts the x-axis at minus 2, 0, 0, 0, and 2, 0. Therefore, the zeros of the cubic polynomial x cube minus 4x are x-coordinates of the points where the graph of y is equal to x cube minus 4x intersects the x-axis. Let us consider few more cubic polynomials, x cube and x cube minus x square. This is the graph of x cube, but it intersects the x-axis at only one place. That is, at x equal to 0, it touches the x-axis. Therefore, for x cube, 0 is the only 0. And consider this graph. For y is equal to x cube minus x square. It touches the x-axis at 2 places. One is at the origin, that is, when x is equal to 0, it touches the x-axis, and when x is equal to 1, it touches the x-axis. Therefore, the corresponding coordinates are 0, 0, and 1, 0. So, the number of zeros of the cubic polynomials x cube and x cube minus x square are respectively 1 and 2. So this is the point you have to remember. Given a polynomial p of x of degree n, the graph of y is equal to p of x intersects the x-axis at most n points. Therefore, a polynomial p of x of degree n can have at most n zeros. So this point you have to remember. Now an example. For each of the graphs, find the number of zeros. Only thing you have to find how many times it intersects the x-axis. In the first case, it intersects at exactly one place. Therefore, that corresponding polynomial has only one zero. In the second case, the graph intersects the x-axis at two places. Therefore, the polynomial has two zeros. In the third diagram, the polynomial intersects the x-axis at three places. Therefore, the polynomial has three zeros. Here, it is only 1. And here, it is only 1. Because it touches the x-axis at only one point. Here, the number of zeros is 4. The last diagram, the number of zeros is 4. Now exercise 2.1. For each of the graphs, find the number of zeros. The first diagram, it is a straight line parallel to x-axis. Therefore, it will not touch the x-axis. Therefore, the number of zeros is equal to 0. In the second case, the graph touches x-axis at one place. Therefore, number of zeros is equal to 1. In the third diagram, number of zeros is equal to 3. Number of zeros is equal to 2 here. Next number of zeros is equal to 4 here. Next number of zeros is equal to 3. Now we are going to study an important relationship between zeros and coefficients of a polynomial. Look at this table. First we take a linear polynomial ax plus b. It can have only one zero. Say it alpha. Then what is alpha? Alpha is equal to minus b by a. If you take this value is equal to 0, then x is equal to minus b by a. That is alpha is equal to minus b by a. What is minus b? It is constant term. What is a? Coefficient of x. Therefore, this is the relation between zeros and coefficients for a linear polynomial. Suppose it is a quadratic polynomial ax square plus bx plus c. You can take alpha and beta as their zeros. In that case, sum of zeros is equal to alpha plus beta, which is equal to minus b by a, which is equal to minus coefficient of x divided by coefficient of x square. Product of zeros is equal to alpha beta, which is equal to c by a. What is that? C? Constant term. A is coefficient of x square. So, two are the relationship between the zeros and the coefficients of ax square plus bx plus c. Now you look at the cubic polynomial ax cube plus bx square plus cx plus d. Let alpha, beta, gamma be its zeros. In that case, sum of the zeros alpha plus beta plus gamma is equal to minus b by a. So the first relationship starts with the minus sign, negative sign, minus b by a, which is equal to minus coefficient of x square divided by coefficient of x cube. Next, alpha beta plus alpha gamma plus beta gamma. Sum of the zeros taken two at a time, which is equal to c by a, which is coefficient of x divided by coefficient of x cube. Next, product of the zeros alpha beta gamma, which is equal to minus d by a, that is minus constant term divided by coefficient of x cube. So these are the relationship between zeros and coefficients. This you have to remember. Now, example 1. Find the zeros of the quadratic polynomial 2x square minus 8x plus 6 and verify the relationship between the zeros and the coefficients. Solution. Let us rewrite 2x square minus 8x plus 6 is equal to 2x square minus 6 minus 2x plus 6. We should know how to separate minus 8x. You have to separate minus 8x. You have to find two numbers so that its product is 2 into 6, which is equal to 12. Sum is equal to minus 8. In that way, you have to separate the middle term minus 8x. I have written that as minus 6x minus 2x. So minus 6 into minus 2 is 12. And minus 6 minus 2 is minus 8. Now, in the first two terms, 2x is common. You take it outside. 2x into x minus 3. Here, minus 2 is common. Take it outside. So, minus 2 into x minus 3. Now, x minus 3 is common in both the terms. So, you can write it as x minus 3 into 2x minus 2. Here, 2 is common. Again, you take 2 outside. You get 2 into x minus 3 into x minus 1. So, when x is equal to 3, this term becomes 0. When x is equal to 1, this term becomes 0. Therefore, for the polynomial 2x square minus 8x plus 6, x equal to 3 and x equal to 1 are the zeros. Now we verify the relationship between the zeros and the coefficients. Sum of zeros is equal to 1 plus 3, which is equal to 4. Now we find minus coefficient of x divided by coefficient of x square. Coefficient of x is minus 8. So minus 8 is plus 8 divided by 2, which is equal to 4. Therefore, the first relationship is verified. Now you see the second relationship. Product of the zeros. 1 into 3 is equal to 3, which is equal to 6 by 2, because 6 is the constant term and 2 is the coefficient of x square. Now let us see the second problem. Find the zeros of the quadratic polynomial x square plus 7x plus 10 and verify the relationship between the zeros and the coefficients. Same way we are going to solve this problem. So what I am going to do? I am going to rewrite the polynomial x square plus 7x plus 10 as x square plus 5x plus 2x plus 10. Here 5 into 2 is equal to 10. 5 plus 2 is equal to 7. So, in such a way, you have to separate the middle term. When you solve more problems, you will be familiar with this idea. Now, x is common in the first two terms. Therefore, you take x outside, you get x into x plus 5. 2 is common in the last two terms. Therefore, 2 into x plus 5. Again, x plus 5 is common. Therefore, it is x plus 5 into x minus 2. Now, minus 2 and minus 5 are the zeros of the given polynomial. We are going to verify the relationship between the zeros and coefficients. Sum of zeros. Minus 2 plus minus 5, which is equal to minus 7. Whether it is equal to minus coefficient of x divided by coefficient of x square? Yes. Minus 7 divided by 1, which is also minus 7. Similarly, product of zeros, which is equal to minus 2 into minus 5, which is equal to 10, equal to 10 by 1, which is equal to constant term divided by coefficient of x square. Hence, the relationships are verified. Now, you consider the third problem. Find the zeros of the polynomial x square minus 3 and verify the relationship between the zeros and the coefficients. Solution. X square minus 3 is equal to x plus root 3 into x minus root 3. Here the middle term is missing. Therefore, you can easily factorize it using the formula x square minus a square is equal to x minus a into x plus a. Therefore, the zeros of the polynomial are square root of 3 and minus square root of 3. Now, we are going to verify the relationships. Sum of the zeros. Root 3 plus minus root 3 is equal to 0, which is equal to 0 by 1, because the x term is missing. Why x term is missing? Its coefficient is 0. Therefore, that term is not present here. So, minus coefficient of x divided by coefficient of x square is equal to 0. Next, product of zeros, which is equal to root 3 into minus root 3, which is minus 3, which is equal to constant term divided by coefficient of x square. Hence the relationships are verified. Consider the fourth problem. Find a quadratic polynomial, the sum and product whose zeros are -3 and 2 respectively. Solution. So let us take alpha and beta as the zeros of the polynomial ax square plus bx plus c. We do not know the value of a, b, c and alpha and beta, but we are given alpha plus beta is equal to -3 and alpha beta is equal to 2. Only two things are given. You have to find out the polynomial. Let us see. So we are given alpha plus beta is equal to -3. You know the relationship between zeros and coefficients. Therefore, it is equal to minus b by a. Similarly, alpha beta is equal to 2, which is equal to c by a. Now, in this equations, if we take a is equal to 1, you can take any value for a, but it is better to assume a is equal to 1. Then obviously b is equal to 3 and c equal to 2. Now you can write down the polynomial. Because a equal to 1, b equal to 3, c equal to 2. Therefore, the polynomial is x square plus 3x plus 2. If you take different value for a, you will get a polynomial like k into x square plus 3x plus 2. That is also correct. K can be any integer. Thank you so much for watching my video.